This lecture is going to cover Chapter 8 and specifically Section 8.4, the sampling distribution of the sample mean. So let's go back and talk about the salmon population again. And this time let's ask a question about this population. Here's our question. Are salmon getting smaller? So in order to answer this question with statistics, what we're going to do is create a statistical hypothesis. So first of all, I want to think about what the theory is. And the theory is based on our question. So our theory might be specifically that the weight of salmon is less than what we currently believe. Now, one of the issues that we have to deal with in statistics is how to take a theory that's articulated in English and convert it to a statistical theory. And one of the ways we can do this is think about this sentence or this theory implying that the true population average, mu, the true population mean, is less than the mean we're hypothesizing, or the mean that we're using in our model. So we would translate this theory as follows. The null is going to remain the status quo, that the actual population mean is mu equal 30, and the alternate is going to be that the true population mean mu is less than 30. And now I have a statistical hypothesis that I can test using data. Now, it's a statistical hypothesis because the null and alternate form dichotomous sets. The null, the way I'm writing the null, is that the mean, the true mean, is 30. The alternate is that the true mean is less than 30. Those two statements can't possibly be true at the same time. So if we find evidence that contradicts the null assumption here, then we'll have to reject the null in favor of the alternate. And that would be, we would call that significant evidence if we meet our standards, namely alpha. We'll get to that later, but that's the basic idea. So when we get our data, we're going to look at it, we're going to analyze the data, and we're going to make a decision about whether or not the null hypothesis is still reasonable. But again, in order to test this hypothesis, I need to catch a sample. So, fish on. Caught a fish. Fish that we caught is 17.4 pounds. So the question is, what do we do now? Well, the question that we need to ask about this particular data value is how rare and unusual is it given that the null hypothesis is true. And the particular statistic that's going to answer this question is the p-value. So let me rewrite the null or the statistical hypothesis that we're considering in this example. So the null hypothesis is that mu is equal to 30. The alternate hypothesis is that mu is less than 30. Sometimes I want to make one point here. I like to write the null with just an equal sign. There's actually two ways to write this null hypothesis. We can also write it as mu is greater than or equal to 30. And then the alternate is that mu is less than 30. I usually write either way is correct. I usually write the hypothesis like this because what you'll begin to see is that when we do the statistical analysis, we're actually going to use the equality part. They're both dichotomies, though. And certainly if we reject at 30, we would still reject at mu is greater than 30. So either of one of those nulls works fine. So when I start to think about a p-value, remember I need three things to calculate the p-value. Okay? So what are those things? Do you remember? Well, we need an observed value. We need the direction of extreme. And we need the null distribution. So these are the three things that we always need when we're going to calculate a p-value. So the observed value is the data value, 17.4 pounds. So let's talk about the direction of extreme here a little bit. So, and the null distribution. Now, I'm going to draw an axis. This is the section 8.4 where drawing and labeling your axis is going to be really useful. Okay, so the label that goes on the axis here is x. Okay, because we have one fish, one weight, and we're going to use that one data value to make a decision. So what am I going to assume about the null? Well, we're going to assume that the null distribution is normal, okay, and centered at 30 because that's what the null hypothesis says. The null hypothesis is telling us that mu is equal to 30. Now, we do have a major issue here. I'm going to bring it up, and that is we always know what the average is or what the mean is for the population because that's by assumption. That's our null hypothesis. But the real issue we have here is realistically, if I'm doing this as a real problem in the real world, I don't really have a measure for the spread, or I don't really know what sigma is. So this is a kind of problematic. So I'm going to have to make an assumption about sigma. Now, there are some ways to get around this. Well, not really. There are, and we're going to talk about the ways to get around this in a minute, or later on in the next lecture. But for now, I'm just going to assume that I know sigma, and this is shaky. I think there's a C in there, shaky. I don't remember how to spell shaky. That's all right. I'm not going to worry about it. Now, now let's talk a little bit. So what I've been building up to here is that is part 3, the null distribution. Okay. Again, we're assuming that mu is equal to 30, so that's okay. So the null distribution, all right, I'm going to assume it, just to do this problem, I'm going to assume that it's the normal 35 distribution. And the other thing we need to talk about is the direction of extreme. Now, this is another interesting situation because the direction of extreme is going to be in the direction where the values on the axis become more common under the alternate than they are under the null. So when I look at this alternate distribution, I don't know, we're not in the alternate, we're not speculating on exactly where the alternate distribution might be centered or pinned down on the axis, but all we're saying is that that distribution is shifted to the left. So the direction of extreme here is one-sided to the left. So I'll make a notation here. Direction of extreme, one-sided to the left. All right. Well, turns out we have everything we need because we do have this data value now. And so if I let me put some scale here on the axis, because again, I'm claiming that I know the alternate, or I'm sorry, the null distribution by assumption. Whoops. Oh, that hurts. Okay, let me redraw this. Every time I click a screen, I lose everything I've written. And so let me redraw this real quick. So let's see, we're saying this is centered at 30, and then 25's here, and 20's here, and 15 is here. And let me just give you a quick sketch. There's where the alternate is. Here's the null, what we're saying the null distribution is, mu equal 30. Okay. A couple more values on here. And so the direction of extremes one-sided to the left. 17.4, I'm going to put right about there. Okay, so that's our observed value. It's about 17.4. So the p-value is going to correspond to the area in this tail. So the p-value here is going to equal, I need to find the area, so I'm going to use normal CDF. Lower limit's going to be negative E99, because it's a left direction of extremes, one-sided to the left, up to the data value, 17.4. The mean is 30, and the standard deviation is 5. So, need the calculator. So let me go and get the TI calculator. All right. Let's see. So I'm going to go second vars to take me to the distribution menu. Choose number 2. Lower limit negative E99. Upper limit is going to be the 17.4 data value. The mean is 30. And the standard deviation is 5. So the p-value we're getting here is about 0.0059. And this is very small. And it would certainly be less than, for example, if I made alpha 1%, then this p-value is clearly less than 1%, and it's less than most reasonable alphas we would use. So the decision here would be to reject H naught. We have statistically significant, or the data provides statistically significant evidence that salmon are smaller than assumed. And again, well, let's go and talk about the situation. So realistically, are we really going to make a decision based on a single fish? And the answer is no, not at all. And the the reason it really makes no sense. Now, of course, as you're learning statistics, dealing with one sample makes the math easier, makes the mathematical reasoning easier. But from a practical point of view, a sample of size 1 is really not going to provide the kind of credibility that we're going to need. For example, one of the reasons I like to talk about salmon as an example is because in Humboldt County, the salmon fishery is part of the economy, and there's always a lot of debate. There's a lot of political wrangling between the people that do the commercial fishing and the fishing game. And these are the kinds of questions that they're grappling with. How healthy is this population of salmon, and that dictates how many fish can be caught and all of those types of things. So it's an important question, but again, if you think about it, the fisher people are going to say to the fish and game, you're really going to make all of these decisions based on one fish? No, no, they're not. So, but when we go to more fish, okay, we do run into some issues. So let's talk about this for a second, because we do have, from previous examples, one sample. And this sample is reflecting 33 fish. That's the sample size. And the sample mean is about 30.51. Okay. And so now, if we're going to make a decision based on this sample, okay, now, and remember that this sample mean that we're talking about, this is a average, the mean of all of these weights. So as a measure of typical, it's much better than one fish for sure. But again, if we go back to our hypothesis test, or our statistical hypothesis, okay, the question that we need to ask is whether or not this particular sample is consistent with the null or inconsistent with the null. And here's our issue. Okay, our issue is that, okay, I'm going to go through the same process I did before, okay, and think about the three things I would need. Again, what we really are interested in, or one of the things that we're really interested in, like before, is the p-value. So if I could, this is really my goal, or one of my goals, is to try to calculate this p-value. Well, the trouble that we're going to have is now I'm labeling my axis with x bar. Now, since the null is that mu is equal to 30, I'll put 30 on that axis, but I hope everybody realizes that it really makes, well, first of all, how can we be sure? Well, I guess my question I want to ask is, should we model x bar using N35, or the normal distribution with a mean of 30 and a standard deviation of 5? And remember, this is x. This is what we said about x. But is x bar's distribution the same as x's distribution? This is the question that we need to investigate. Now, what we've done in the past in this class is when we've been interested in a question like this, what's the distribution? One of the things we've done is simulate it. So we have one sample and one sample mean, but let's take another sample, okay? Again, remember, we're assuming, okay, we're assuming x is normally distributed with a mean of 30 and a standard deviation of 5. So I can sample, mathematically, I can sample from this distribution as follows. Use rand norm, okay, and 30 comma 5, this will give me one sample. If I put a 33 at the end here, I'll get 33 means. Or I'm sorry, not 33 means. I'll get 33, okay? So let me be clear here. This is N equals 33. This is sigma equal 5. And this is mu equal 30. So what random norm is going to produce is a set of 33 x values. And then I can take the mean of that set, and that will give me a particular sample mean value. So let me go to the calculator. So if I go to math, go to PRB, choose random norm, 30 is the mean, and again, this is by assumption, but remember, we're modeling the null hypothesis, so it's okay. There is one issue here, and that's the sigma, but I'll talk about that later. So right now, what I've just done is collected a sample from a mathematical distribution, a normal distribution with a mean of 30 and a standard deviation of 5. So I have 33 data values in this set. And what I'm interested in is the mean. So I'm just going to go, and all I'm focused on right now is the sample mean. So I'll take the sample mean of this answer. And what I end up with now is another mean that came from this assumed population. Okay? And the simulation part comes in like this. Okay? I'm going to repeat this process of sampling over and over again. And I'm going to, by doing that, by repeating that process, I'm going to collect a set of sample means. And then I can draw a histogram of that set of sample means and start to see what that distribution might look like and compare it to the distribution for x. So the important thing to see here is that we're comparing the distribution that we're sampling from, x's distribution. We want to compare that to x bar's distribution. So let me show you a couple of tricks here. So first of all, I can automate this a little bit by taking the mean and the random sample at the same time. So the calculator will actually allow me to embed the random norm function in mean and do those two steps in one. So there's another sample mean. And now that I have the syntax set up for sampling and calculating the mean, all I have to do is press enter, and the calculator will start to print out sample means. Now these are sample means based on a normal distribution with a population mean of 30 and a population standard deviation of 5 and a sample size of 33. So I understand this is complicated, what we're doing, okay? So I could continue to collect these sample means, and what I would do, the idea here is that I would, because remember what we're interested in is here's our question that we're trying to address. What's x bar's distribution? Because if I'm going to calculate a p-value, this is what I need. I need the distribution. And again, like I want to reiterate, I want to make sure I'm being very clear. We're assuming that x is normally distributed with a mean of 30 and a standard deviation of 5, but the question that we're asking is, what is x bar's distribution? So x bar is what? What is x bar's distribution? So that's what we're investigating. Now, the simulation aspect is going to work like this, okay? Now, if x is continuous, x bar is certainly continuous as well. But as I investigate, x bar's distribution, I can do so by using a frequency plot. So in other words, and again, eventually, instead of a frequency plot, the version of the frequency plot I'm going to use is a histogram. So as I take these samples and calculate these sample means, what I'm going to do is plot those up using a histogram. And I kind of started to draw a frequency plot here just to give the idea. But again, we're going to turn those into bars and look at the distribution in terms of a histogram. So that's kind of where we're going. And we're going to use the calculator to facilitate this because, see, again, I can calculate these sample means relatively easily. But even at that, even by doing it this way, it's still quite a bit of work and takes quite a bit of time. So what I've done is I've actually written a program that will automate this process. So let's run the program. So they enter the population mean. So the population mean we're using here is 30. Population standard deviation that we're using is 5. And we're modeling sample means from samples of size 33. Now, the calculator doesn't have mu, sigma, and lowercase n built in. So these are m, s, and n are internal variables to the program. So I used m for mu. Mu is a Greek m, so it kind of makes sense. Capital S is sigma, and capital N is really lowercase n, but I don't really have an option on the calculator to use any other n. And then I want to talk about the number of samples. So number of samples is going to be the how many times I do the simulation, or how many samples that I get. And so let's start off easy. We'll do 20. And so what the calculator is doing right now is that same process I did on the home screen, where I did the random norm and then took the mean of that sample. So these are all sample means that are being printed out. And then I wrote the program so those sample means would be stored in a list called means. So what we want to do now is compare X's distribution with X bar's distribution. So I'm going to draw a couple of histograms, okay? So let's see. The first histogram I want to draw is the original data set that we were analyzing before, where our first sample mean came from, the king salmon data set. So I already have my window all configured. I'm going to, the statistical plot window configured. So is this the window I want to use? Let's see what this looks like. All right, so I've spread this out a little bit more, okay? And again, you can see it looks like it's a pretty normal looking type of a distribution. And again, this data set came from a mathematically perfectly normal distribution. And it starts at 10 and is scaled by 2s. Okay, so we got that down. Now, the other stat. So what I want to do, so this is just one sample of 33, and the axis right now we would label with X. And what I want to do is compare that with X bar, X bar's distribution. So I'm going to superimpose this other histogram on top. So I'm just going to turn on, and then this is going to be a histogram of those sample means. All right, so those two graphs are drawn together. So they're kind of, it's hard to tell which one's which. So let me go ahead and turn plot 1 off, which was the X histogram, and take a look at X bars. Now, that's kind of a profound thing, because notice that those sample means are clustered really tightly together. So when I go back and I look at the comparison here between these two, okay, and remember the scaling goes like this. So this one started at 10 and it went to 12, and then this is 14, and then this is 16, and this is 18, and this is 20, etc. I'm not going to rescale the whole axis, but this is this is an x-axis now, and then this axis is X bar. Okay, and it has the same scaling, so this would be 10, 12, 14, 16, and so on. Notice a couple of things. If I were going to balance this distribution on a single point, of course that's going to balance on the sample mean. and I'm going to balance this distribution on a single point. If you look, those two distributions seem to balance at the same place. Now, I don't think we want to say that that the distribution for x and the distribution for x bar are the same, though, because the glaring difference that I'm seeing is that there's way more spread for the histogram of x, the x distribution, than there is for x bar. Okay, so there's definitely, it's clear that, to me now, at least I hope it's clear to you, that x and x bar have different distributions. And the very first thing, now it looks like they're centered pretty much on the same value, but the spread is not the same here. So there's definitely an issue that we're going to have to work through. Now, the other thing I want to think about is what's the shape of x bar's distribution? So again, if I go back to the calculator, now the scaling on this window is a little bit funky because again, there's only 3 bars here. There were many more bars with the x distribution. So I'm going to change up my window here a little bit, and I'm going to narrow it just to get more resolution, or I want to divide that axis up. I want to make my class width smaller so I get more bars. And I also want to narrow this window. And what that's going to do is spread out my distribution. So let's see, I'm going to start with 20. I'll just make it 20 to 40 for starters here. And let me make this x scale 1, and that's going to cut the class width in half. Okay, so now we're starting to see a little more shape to that graph. The other thing I want to do, I'm going to go back and run this program again because I only have 20 samples here. So let's do more. Let's take just a minute. This program's pretty fast. Of course, it'd be faster on a microcomputer instead of a calculator, but nonetheless, let's see. So let's do 100. So we're gonna take 100 samples of size 33. Okay, and it's going to take it a minute or two. So sit back here and let the calculator do its work. So all of those numbers scrolling by on the calculator screen are sample means. Okay, so we have 100 sample means stored in list means. Now I'm going to go back and look at the graph, okay? And again, I need to change my Y max here because Y max on the current screen is only 12. So let me go in here and change the 12 to say 25 maybe. Still not enough. The other thing I'm noticing is, look at the spread here. So we've got a lot of axis here that clearly is not being used by this particular histogram. So I'm going to come in here and I'm going to narrow that window even more. I'm going to go 25 to 35. And notice I'm keeping the X window centered on 30. And I'm going to cut that class width down to 0.5. Take a look at the graph. All right, that 1 bar still wants to go up off the top here, but let's see. Let me see if I can. And again, this is I just got these means, so I've got to play with the window and get it set up correctly. Okay, that looks pretty good. So let me take a screenshot of that, and I'll bring it back over to my PowerPoint slide and paste it in. Okay, so specifically now again, the two above here, these two graphs are comparable because they have the same scaling on their axis. And then the one here down below, I've modified the axis a little bit. So let's talk about this. So let's see. So first of all, this axis would be labeled with x. This axis would be labeled with x bar. And this axis would also be labeled with x bar, but the scaling is different. So the two graphs above are demonstrating that, again, this looks like, well, it did come from a normal distribution. So this data set that we started with originally, because I sampled it for the very beginning, I sampled it from a known normal distribution. But one of the things that's clear to me from these graphs, or is becoming clear, is that the spread between these two distributions is not the same. So we can't model x bar using x's distribution. And then the other question I'm looking at, or the other thing I'm seeing here, as I zoomed in on the x bar histogram, that it looks to me that the sample means are also following a normal distribution, but it's not the same normal distribution, okay? And that stands to reason. I mean, if we're sampling from a mathematically perfect normal distribution and looking at the distributions of the sample means, it makes some intuitive sense that the distribution of sample means will also be normal. Well, all of this is complicated, okay? But let's go into some definitions now. What we've been talking about is the sampling distribution of the sample mean. And the definition is the distribution of values of the sample mean in all possible random samples of size n. Same size n taken from the population. And notice on the calculator, that's exactly what I did when I did the simulation. But I certainly did not do all possible random samples. There are an infinite number of possible random samples in this scenario, so I can't really possibly simulate this. The simulation gives me an idea about what the distribution looks like, and it is giving me also evidence that x bar and x have different distributions. Now, let's talk about the central limit theorem, the CLT. It's a very important theorem. Central limit theorem. It's a central theorem to all of statistics, really. So let's talk about this. All right. This is addressing the sampling distribution of x bar. So if simple random samples of size n are taken from a population having a population mean mu and population standard deviation sigma, then the sampling distribution of the sample mean has the following properties. Number one, mu sub x bar equals mu. All right. Well, when I go back and look at these histograms, that was the idea about the two distributions being centered or balancing on the same value, okay? And again, we're looking, these are sample means. So of course, this particular distribution is balancing on its sample mean, but it looks like these two histograms would balance on the same point, and that is alluding to this concept that the population mean of the sample means is equal to the original population mean. So that's this first part of the central limit theorem, that the mean, the center of the distribution for x bar is the same as the center for the x's distribution. Number two, and this is, number two is very important for our calculations. Okay, it tells us how to adjust the standard deviation. So what we were seeing in our histogram is reflected in the CLT, the central limit theorem. The standard deviation of all the possible sample mean values decreases as the sample size increases. And there's actually a formula we can use. And the formula is given right here. The population standard deviation for x bar. So again, x bar is a subscript here. It's like a accessory for the symbol sigma. And again, sigma here has no subscript. I could put a subscript on it maybe to be clear. Okay, if I did, it would be x. So the population standard deviation for x, or for x bar, the population standard deviation for x bar is equal to the population standard deviation for x divided by the square root of n. And notice mathematically, as n increases down here in the denominator, even though it's being square rooted, it's still, as it increases, the square root of n increases. And when I have a fraction with the denominator getting bigger, the overall fraction gets smaller. So sigma sub x bar is going to be less than sigma sub x. And this formula tells me exactly how to adjust the standard deviation when we're modeling x bar. So now we're modeling the sample mean, so we need to adjust the standard deviation. And then part 3 tells me about specifically what the distribution for x bar is. So part 3 of the central limit theorem tells us that if the original population is normally distributed, then for any sample size n, the distribution of the sample mean is also normal. And it's going to have the given mean and standard deviation. So paraphrasing 3 mathematically, okay, if x is in mu sigma, then x bar is in mu sigma over the square root of n. Okay, so for the salmon example, x is in 35, so x bar is in 30, 5 divided by the square root of 33. So now that I have the central limit theorem, I actually have a way that I can go back and model that sample mean. So if I go back to the original problem that we had here, okay, and I can actually do the calculation. So I can say, okay, h naught mu equals 30. h1, the theory is that the population mean is smaller. Direction of extreme, we've already talked about this. The direction of extreme here is one-sided to the left. Okay, we have an observed value, that's our sample mean, and we also need the distribution. So x bar is normally distributed, centered at the same mean as the population, but we need to adjust the standard deviation by dividing it by the square root of the sample size. So now I'm in a position now with the central limit theorem to actually calculate the p-value. Okay, so this is just a really rough sketch here, but this is x bar centered at 30, okay, that's what the central limit theorem says. And so what I need to do now is find the area to the left of 30.51, which is over here. And I can already see that that p-value is going to be less, or that p-value is going to be greater than 50%. So this particular data set is not going to give us any evidence that we should reject the null. But let's go ahead and do the calculation. Okay, so the p-value here, and again, this is all based on the fact that the direction of extreme is one-sided to the left. So we're going to use normal CDF. Lower limit, negative E99. Upper limit is the sample mean now. Mu is 30. Standard deviation we're going to adjust. 5 divided by the square root of 33. So let me get the calculator out here, and we'll actually calculate this p-value. So second vars for the distribution menu. Choice 2 is normal CDF, negative E99. So that's second comma E99, really small number. 30.51 was the sample mean. .30 is the population mean. Then I adjust the standard deviation. 5 divided by the square root of 33. Okay, so, all right, so my pretty print might give me some problems. I don't want that parenthesis there. I have to arrow. All right, and then close parenthesis. Okay, I think I got it now. So yeah, the p-value is like 0.72. So it's a really big p-value. There's no way we can reject H naught here. There's no statistical evidence. Now, that should stand to reason, because if you think all the way back to when I originally did this problem, the salmon weights were these salmon weights. This set of data was sampled from N35. So to get it, so it turns out that the null is true. This implies the fact that I sampled this data implies that the null hypothesis is true. So the fact that I took a sample from the null, or I mean from the null distribution, and ended up not rejecting the null, that's a good thing. Now, again, this is what type 1 error is all about, though, because it's certainly possible for me to take a sample of size 33 from this known population and end up with a significant sample mean. It's just that it shouldn't happen very often. Type 1 error rate is what dictates how often that will happen. Okay, so this is where we were at on the central limit theorem. Now there is one more piece of it, which is if the original population is not necessarily normally distributed. This means it's skewed to the left or to the right, but we have a large enough sample size. The distribution of the sample mean is approximately normal. So and the book has some really nice pictures, and please go and look at, read this section carefully, chapter 10, or section 8.4, I mean. And what this is saying is that if say X is really skewed to the left, perhaps, okay, if N is sufficiently large, and what the standard here is at least 30, okay, then what the central limit theorem is telling us is that we can actually model X bar using a normal distribution. So it's really kind of an amazing result, and it's really useful. Now again, both of these things are going to even a skewed distribution has a population mean. Okay, so those population means are going to be the same. It's just that X bar is approximately normally distributed, and we make the same adjustment to the standard deviation. So what you really have to focus on, if you're dealing with a population you believe is skewed to the left or skewed to the right, then you want to pay attention to the sample size and make sure that the sample size is large enough to engage the fourth part of the central limit theorem here. Again, very complicated stuff. Let's take a look at another example, okay? Testing a hypothesis about the mean weight of nuts. 1 pound cans of nuts are to contain a net weight of 16 ounces, but there is considerable variability from can to can. Past records indicate that net weights are normally distributed with a standard deviation of a half a pound. The production manager would like to test the hypothesis of underfilling for the recently produced batch of cans. The null would be mu is equal to 16. The alternate is mu is less than 16. Mu is the mean weight of all cans in the batch. The alternative hypothesis tells us that the direction of extreme is one-sided to the left, and of course we're going to need this to calculate the p-value. A random sample of 6 cans is obtained, and the observed sample mean weight was 15.8 ounces. So what we're being given in the problem, okay, is that the weights are normally distributed. So X is going to be, I'm going to be specific, the weight of nuts in a single randomly selected can of nuts, okay? We're given that X is normally distributed with a mean of 16 ounces. Okay, and that's in the null assumption. And then we have this issue of standard deviation. Well, a half a pound is 8 ounces. There's a unit issue here. There's no way that the standard deviation can be a half a pound, because a half a pound, that means that, you know, if we went 2 standard deviations, we'd be 0 to 2 standard deviations would be 0 to 32 ounces. That's kind of crazy. So I really think this is a typo in the problem, and I'm gonna just modify this to be ounces and ounces. Now, one of the things you want to keep your eye on here as you do these problems are units, and we could do the problem by doing the unit conversion. In other words, I could say this is, you know, normally distributed with a mean of 16 and a standard deviation of 8 ounces, and that would be doing the unit conversion. But I'm gonna modify it because I do think that's a typo. So I'm gonna say, okay, well, actually, let's just go with what the book says, and I'm not sure actually if this is a typo or not, but I'm just going to put 8 ounces in there and see what happens, because that is what's given in the problem, I suppose. So let's just stick with pounds, and we'll convert it to ounces and see what happens. But anyway, I definitely want to point out the unit issue here, and what we do about the unit issue is either do the unit conversions and roll with the problem as it's given, or, and again, as a practical matter, I would go and do research here and ask, and what we would do as statisticians is find out, is that a mistake or is it actually correct? But let's just go ahead and use 16 for the mean and 8 for the standard deviation and see what happens here. Okay, so now the sample mean is given, so we have an observed value, but the question is, what is X bar's distribution? Well, x bar, since the x is normally distributed, x bar is also going to be normally distributed regardless of sample size. But I'm going to have to adjust the standard deviation by dividing the population standard deviation by the square root of n. And in here, so here's a random sample of 6 cans, so n is 6. So this is x bar's distribution. So, and the other thing we're given here is the sample mean is 15.8 ounces. Is this sufficient evidence at the 5% significance level to conclude that the batch had a problem with underfilling? So, Part A, in testing hypothesis, we examine the data on the assumption that H0 is true. If the true mean weight is 16 ounces, what's the distribution for the sample mean? So I already wrote that down in the previous screen, but let me write it down again. X bar is normally distributed, mean is the same, and the standard deviation is adjusted by dividing it by the square root of 6. And I want to point out one thing again that I haven't said enough probably in this lecture. I've said it several times before though in different lectures. X bar is a statistic, and that means it's a variable. So again, I want to make the point that we're always modeling a variable, but in this case now we're moving on to a more complicated situation where the statistics the variable that we're modeling, and this is the distribution for that variable x bar. So now we're going to actually calculate the p-value. So let me go through this carefully. So the null hypothesis here is that the mean weight is 16. And we're going to figure out, or we want to see if that sample mean gives us evidence that the mean weight is actually less than 16. X bar is in, whoops, that should be a parenthesis, in 16, 8 over the square root of 6. So we have x bar's distribution. And then we also need direction of extreme. That's one-sided to the left. So as I think about calculating this p-value, okay, I'm thinking about x bar's distribution centered on 16. I like to draw these graphs. I'm not gonna scale it carefully this time, but I do want to point out that 15.8 is to the left of 16. So the area we're looking for is the area in this left tail, and that area corresponds to the p-value. So to calculate the p-value here, I need to actually find the area in the left tail. It's some normal CDF problem. Lower limits negative E99, upper limits the 15.8 value, and mean is 16. Standard deviation is 8 divided by the square root of 6. So we're going to need the calculator. Second bars takes me to the distribution menu. Oops, that should be 50. I could have swore I pressed the 1 there. 15.8. Hypothesized mean for the population 16. Standard deviation's 8 divided by the square root of 6. Oops, I did that again. Hold on now. I need to do a right arrow to get out from under that radical and then close the parentheses. And the p-value is about 0.47558. So it's clearly eight 0.48, say, I guess, if I remember right now. So, but either way, this is a big p-value. So no evidence against the null. So we cannot. So the decision here is to not reject. And again, I think this is another. Go on here and see part C. State your decision and conclusion in terms of the problem. So what we would say here is that there is no statistically significant evidence that the machine is underfilling the cans. Okay, and that would be, the way the problem's given, that would be the answer, again. But I do have this question about the standard deviation actually being 8 pounds. And if we go back now and we think about it, I'm just going to quickly redo the problem. And this is one of the things that's kind of cool. If I redo the problem now, oops, I'm going back to 30 from the salmon, that's 16. So if I go back and I look at that typo, or if I consider that a typo and say, you know, they meant to say ounces, 0.5 ounces, this is going to make a huge difference, because then x bar, if that was actually a typo, then x bar would be normally distributed with a mean of 16, and then 0.5 divided by the square root of 6. So just for fun, and again, I don't need to redraw the graph necessarily, because all that would change about the problem was 15.8 was that sample mean, 16.5 over the square root of 6. So now, just for fun, let's go back here. And I'm just going to go a second enter, brings back the previous command, because all I need to change here is the 8. So I'm going to go in and change the 8 to point. Second, delete to put the calculator in insert mode. So 0.5 over the square root of 6. And okay, so either way, the p-value here is about 16%. So either way, we have no evidence. So again, this is one of the ways you can deal with what you think might be a typo or a mistake in the problem, is to say, okay, I'll do it the way the problem stated. I'll do it again with the typo, or assuming that was a typo, and I still end up with a p-value that's insignificant, failure to reject. Now, I want to talk about one other situation here, because most of the examples I've did here have had a direction of extreme that's one-sided to the left. And I want to take a minute and modify this problem, okay, to do a direction of extreme in the other direction, or to the right. Now, what's going to drive the direction of extreme is the alternate assumption. So if I switch the alternate from mu less than 16 to mu greater than 16, that makes the direction of extreme one-sided to the right now. And basically the theory would be that the machine is putting too many nuts in the can. And you know, that's also a problem would be a problem for a nut manufacturing. Do you manufacture nuts? I guess it'd be a nut processing and packaging facility, whatever. Overfilling is also a problem. So we might test this hypothesis. And I got to make up a sample mean now. So let's just say, I'll just make one up. Let's just say X bar is 16.75. 16 3/4 ounces was the sample mean. Well, to do this calculation, 16.75 is to the right of 16, so, and the direction of extreme would be to the right because of my alternate here. So this would, the p-value would be given as this right tail area. So we would calculate that again using normal CDF. Normal CDF finds the area under a normal curve. But this time I'd put the sample mean as the left boundary, and then this distribution is going eventually all the way out to positive infinity. But again, I can't put positive infinity into the calculator. So what I would do is use E99 instead of negative E99 on the right side. The mean 16, and then the standard deviation, we'll just use the 0.5 square root of 6. And then I could calculate a p-value. But I wanted to, and then maybe I'll go back to the calculator and do this, but I just wanted to point out that if your direction of extreme is one-sided to the right, then instead of having negative E99 on the left, we have positive E99 on the right in our normal CDF. So let's see, let's redo this. Already, okay, so let's see, second vars. And then, let's see, the sample mean I was using, I made up was 16.75. The right boundary I'm going to use is positive E99. Population mean is 16. Population standard deviation is, I'm going to use 0.5 divided by the square root of 6. Again, assuming that the pounds was a typo in this calculation. So here I'd have a small p-value. Okay, so for the problem that for my modified problem, what was that p-value? I forgot already. Here, let's see, it was about 0.0001. This is small, implying that our decision should be reject H naught. All right. Now, very important note right out of the textbook. We perform this test with an unrealistic assumption the population standard deviation is sigma is known to be 0.5. So there, I didn't notice this, but they're confirming that pounds was a typo because they're saying sigma is 0.5. Of course, they don't put units here, which I think is a little bit of a problem because it doesn't allow us to verify for sure they made a typo. But if the population mean is 16 ounces, I don't know. I'm not sure still. I don't know if that's a typo or not, but I'm not going to dwell on it. It doesn't affect the mathematics. But here's the point, okay? In practice, the population standard deviation sigma is not known. So we would estimate it with the sample standard deviation. Replacing the value of sigma with S would change how we find the p-value. Specifically, we can't use a normal distribution anymore. But another distribution called the t-distribution is used. We will still use the p-value for making the decision in the same way. So that's what makes the p-value so universal. Every hypothesis test culminates in this p-value, and the interpretation, or the way we interpret the p-value, is always the same. We compare the p-value to the specified alpha in the problem. Okay, so the next lecture is going to be about Chapter 10, and be looking for that on the webpage because I'm going to do that lecture real soon. Okay. Well, anyway, hope this is all making sense. I know it's complicated. So have a good day.